Hi everyone, and welcome to another seminar of Physics Latam. Today we are very happy to have Pierre Vanhove. He's a professor at IPhT, Saclay in France, and he will give a talk on methods for computing observables in classical gravity. Please remember to raise your hand if you have any question, and I will leave you with Pierre. Please go ahead.
Okay, so thank you very much for the invitation. And so I will talk about what is indicated in the title is that I will give method for computing observables in classical gravity. And what I will do is that I will try to convey the ideas that are behind the most recent development that the field of post-Newtonian and post-Minkowskian expansion has experienced in the recent years under the impulsion of new techniques from scattering amplitude method. So, of course, I will give you a few nice result that we obtained, but this lecture is more about like the ideas and the method. So this is why I've put this quote by Landau that says that a method is better than a discovery, because with this is exactly what the field is using in order to push the high precision evaluation for gravitational waves. So I don't know if you are all familiar with this physics of gravitational waves, so I will flash a few slides about the motivation. Is that so we now are detecting quite a few events of gravitational waves emitted by the in spiral, and then the merging are either two black holes or black holes and neutron star or neutron stars. Okay. And here there is the typical signal that was in fact detected by LIGO. Now we have LIGO and Virgo data as example. And this is a prediction of Einstein's theory of gravity. So okay, so there is a prediction of what the signal could look like if you use classical Einstein gravity, because here we are talking a priori about classical physics. But the events involve these very intriguing objects that are the black holes. So the black holes, they are not just like static in that case. As you may already be familiar, that they move in our space-time. They move in spiral and then they merge. And as well, these objects, they are pretty far away from us. So the gravitational wave signal that we detect on Earth has been emitted from a source, either these two black holes or neutron stars, okay? And then, there's a propagation of the gravitational wave signal, and then in case, for example, you have neutron stars, you have as well a possibility of detecting the event through light, X-ray, or other signal that are different from the gravitational one. And then you can test whether or not your gravitational wave has propagated between the source of your, it has been emitted to the detector. So in fact, this is not this analysis of the spectrum here. So you have a spectrum. That's something that you try to detect on Earth. We try to do as much as we want, as much precise measurement. It's precision physics. Normally, this is something we use in particle physics, but in that case, gravity, to try to understand whether or not what we detect is fully compatible with what can be computed within Einstein's equation, okay, solving Einstein's equation and predicting the waveform for the emitted gravitational waves. and as well the possibility of testing if something happens in the space, because this is actually the events are quite far away. Yeah, apparently there's a question in the chat, but okay, okay, let's see. Okay, is there a question? Okay, sorry. Okay, so there is and testing whether or not actually all the signal we detect is fully compatible with Einstein ferrogravity or if there is something else. So in a sense, I mean, the method I will try to explain, they are coming from quantum field theory. They treat Einstein gravity that you have here as the first term of an effective field theory. So of course, the main point of that lecture is to reproduce to be useful to classical gravity. But in fact, I mean, at some point in the lecture, and I hope I will be able to reach that point, we can keep something that goes beyond Einstein gravity. So in fact, I mean, from we have lot of more data, and if we understand very well this signal, there's a chance of probing actually the physics of gravity beyond what Einstein gravity gives to you. So this is the large goal motivation for doing this from this point of view of that I'm using. Yeah, is there any question? Or okay, hello? Okay, I don't. Excuse me. Okay, so anyway, so the so this is so in fact, I mean, here, for example, this is one case. I'm still trying to motivate a bit what I'm going to say, and then after that, that will be more on the formal side. So this is a map of the event of gravitational wave event that has been detected, and you see that there is some bond, some what's called mass gap. So actually the black hole that are involved into this merging, they are essentially in that zone. And you don't expect black holes in that zone because they would be too small. And in fact, the formation of these black holes from stellar evolution, I mean, kind of forbids, I mean, black holes to be in that band. And as well, you don't want to have as well black holes that are too heavy. Okay, so normally there is the standard theory that the way we understand how these black holes are formed in the universe, and then a lot of the events they fit in what we already understand about that, the population of the black holes. Except that recently, so this is an event that from the 23rd of November 2023. It seems that there could be some event in this very small black hole band, which is a puzzle. So in a sense, I mean, it's not clear if this is really a confirmed gravitational waves event from merging of black holes, then the origin of these small black holes is very unclear. So this is a question. So then if you trust the signal that you have detected, then that opens a question about the physics of black hole. And then there is as well some some very heavy black hole detection that are actually sitting in that band. So as well, there is a lower band, there is an upper band question. So apparently there is an event where a super huge black hole merger has been detected of 225 solar mass. And in fact, it seems that, and as well, their spin is extremely high, very close to the extremality bound for the maximal spinning of the black holes. So again, these very heavy black holes are not, I mean, their origin is not understood. So in fact, I mean, this is telling you that everything that I'm going to tell you about these techniques that allows you to produce waveforms or other observables associated to this signal is really, really just not, I mean, trying to push to the next order some post-Newtonian and post-Minkowskian expansion. Is really probing the physics of gravity beyond the classical theory of Einstein theory. First, I mean, understanding as well the population of these black holes that are in the universe, and there are a lot of black holes everywhere in the universe. This is one thing. The second thing is that this is as well maybe opening question toward beyond Einstein gravity question. So what can we do? So in fact, I mean, this is when you have the two black holes or two massive objects that are in spiral. So there is a phase which is called in spiral phase. This phase actually is a perturbative regime. So you can treat that phase using perturbation. So there are two ways that people use. There's one what is called the post-Newtonian expansion, that is an expansion in the gravitational strength, okay, small g expansion. So it's a weak coupling expansion. And there's as well a small velocity expansion. So the relative velocity between the two objects, if you use virial theorem that equates the kinetic energy to the gravitational potential, you see that V square is the order of G m Newton constant times the total mass, okay, divided by R. So you can do an expansion in both quantities. Or, and this is more what I'm going to explain to you, is that you want just to do a perturbative expansion, so you just weak coupling, but you keep a totally relativistic regime. So that means you are in a regime where you want a computation that is valid from the static case, so the two massive objects, they are just static, they don't move, to the case where they are ultra relativistic. So in a sense, I mean, this is why you need, which we need here, a high order resummation of the velocity. So the post-Minkowskian is just expansion in G and valid for all velocities. And there is another expansion that I will tell at the end, is that which is when one object has a very small mass compared to the other one. So in a sense, this is a small object behaving into the curved background created by the heavy one. So in that case, here, the post-Minkowskian expansion, it's like flat space expansion. So we are in flat space, and then you compute the mutual interaction between the two objects. So you don't really see the fact that there is the black hole metric, I mean, that is involved. I mean, so the self-force expansion makes explicit the fact that there is really a curved space metric that is given by a black hole, and then another mass that moves into that curved background. It's called the self-force expansion. So these two these two approaches, two and three, they are, that will be the topic of this lecture, and they are the one that I've seen a lot of new result and coming from the amplitude community. And as I said, I mean, the point is that you want to have something that is, so this is G Newton, this is the velocity. So you want to have here a computation that allows you to study your event, I mean, in all range of velocities. So you may have heard that indeed, I mean, no, these days, I mean, thanks to the method I'm going to explain, we have been going to pretty far in the perturbation. And so 5 p.m. mean 4 loops. So this is the cover of Nature and the computation by a group in Berlin, where they did, indeed, they computed the waveform to some high order and perturbation. And the reason is that you need to go, there's an estimate that you need to go to some certain order and perturbation, which is actually the sixth post-Minkowskian order, that will be enough so that where you can still approximate the black hole by point particle. So everything that is going to be said in that lecture will apply. And that will be needed for high precision analysis of the gravitational waves detection, especially when we will have LISA in space. Okay. So now let me try to explain exactly what is this post-Minkowskian expansion. Okay, and we have a system, yeah, two massive objects. They interact and they radiate. Okay, so you are certainly familiar with the problem of the electron and the equivalent in atomic physics, right? So you have an electron that is orbiting the nucleus and a priori classically radiates energy, and you quantize it, and then the atom is stabilized. So here, actually, what we are really interested is a bond state problem, where you have two objects that have some special type of orbit, and at some point they will merge. But this is a dissipative system. I mean that emits radiation, gravitational radiation. Okay, so this is and then because they radiate, I mean the two objects, they come closer together, and then at the end they merge. So you build an operator H that has some level of energy. In the center of mass, okay, there's p squared divided by the total mass, and then there's a central potential. Okay, so this is first to introduce some and then the, oh, I'm sorry, that should be V, not H. So the potential is G Newton times 1 over R. Okay, so this is the operator. So of course, what we do is that normally you are interested by the bond state problem when you have a discrete spectrum. Okay, but what I will do is in this lecture, I will explain to you about the scattering. So I will discuss the scattering of the two massive objects. So the scattering regime, I mean, means that you have plane waves, you have a continuous spectrum, but there is at the end a way to convert this to the bond state regime, which is really the problem you want to solve. And that would go through computing some specific observables, in particular the scattering angle that one computes, that we can go from the scattering regime to the bond state regime. But okay, let's start. Okay. So we have an Hamiltonian. So we want to build an Hamiltonian that I call PM, which is for post-Minkowskian. So I have my two massive objects that are mass M1 and mass M2. So here I am putting myself in the center of mass, so P square, and then there's a potential V. So this potential V is a relativistic potential. And in fact, okay, so as I said, I'm going to treat this question using perturbation. So this is an expansion in power of G Newton, okay? So the first order, of course, of the expansion of the potential is G Newton to the 1. So this is why it starts with G Newton to the 1. And I've decided to have a label L0 G Newton to the 1 L plus 1, because you will come in a minute that actually the power of G Newton is loop plus 1. So when I said that 5 p.m. is for loop, 5 p.m. means G Newton to the fifth, and loop equal 4. Okay, so so G Newton to the 1 means 0 loop. That will be 3 level, as you will see in a minute, and etc. Now, this potential is, okay, so the first order of the potential is G Newton divided by R. So this is the Newton's potential between two massive particles. So in the static case, when the two objects don't move, the factor gamma is 1. So 2 gamma square minus 1 is 1. So you get minus g Newton m1 square m2 square divided by r. So this is the energy. Yeah, this is the energy of the particle. So these factors are just the mass. So in fact, this is the this is the relativistic generalization of Newton's potential. So when you have your two objects of mass m1 and m2, they move at a relative velocity v, so p1 dot p2. So in terms of the momentum, p1 and p2, p1 dot p2 divided by m1 m2 is the relativistic factor, the way it's defined. But this potential in Einstein general relativity has corrections. As you know, it gets correction to higher order in g Newton, so g squared, g cubed, etc. It's the higher order correction in g Newton, they are suppressed by higher order inverse powers of the distance between the two massive objects. And here there is something extremely important, is that the dependence on the mass of the object. So when you consider the higher order corrections, so the correction beyond Newtonian, the Newtonian potential, you have here something that depends, it's a polynomial in the masses. In fact, so there is no log of the mass, there is no overfunction. It is polynomial in the mass, m1, m2, as you see. It has, by dimension analysis, the property that the total degree of the mass dependence is determined by actually the order of g Newton where you are working with. That's one thing. And here there are the coefficients that are velocity dependent. Okay, so again, I repeat, so when L equals 0, this is V1. So in fact, you just have a factor that is this simple factor, but of course, at higher orders in G Newton, the difficulty is to compute exactly what is V gamma. So if I want here to be able to understand what's happening here to higher order perturbation and actually even have a computation that is valid very close to the merger, because of course when I am here at the merger, the computation is not perturbative anymore, so I have to use a numerical GR or something else. I need to go to some order in perturbation, and I want to compute what is V, right? So when I have the H and I have the V's, I have the potential, and then I can study my bond state problem. Okay, so this is essentially what I want to do. So the idea behind the method that I'm presenting in this lecture, they are not new because you see in 1978, Kovacs and Thorne, they already stressed that any classical problem can be solved using quantum mechanics method. And the reason is that they say that sometimes it's easy, they are easy, some problem is easier, it's easily to solve using quantum field theory methods. And they knew that actually Feynman integrals would be useful. Except that in 78, the technology for computing scattering amplitude was not as developed as it is today. So today we have developed a lot this field because of essentially motivation from precision physics for the Higgs. And so there's a lot of new methods and ideas that were unknown to Kip Thorne and Sandor Kovacs at the time when they wrote that paper. But at the end of the day, the idea is the following. So what you do is that you do a scattering, because if you use Feynman integral, okay, so then you do a scattering, particle 1, particle 2, they scatter gravitationally, so inside there is only gravitational interaction. And so this is a quantum amplitude. And you define an appropriate classical limit. How you do that is precisely, is not a trivial fact, so this is what I'm going to explain. Then you get a quantity that you call a classical amplitude, from which you build the contribution, because this computation is done at some fixed order in G Newton, but a priori your computation is relativistically invariant, and then you get from this, and then you build a quantity that exactly you are adding a next order in your potential. So you complete your Hamiltonian. So the idea is so this is a graph here. For example, here I have two lines. I have an object that has a momentum P1, mass M1, spin S1, okay? Another massive object of momentum P2, mass M2, spin S2, that exchanges gravitationally. So this is only gravitons. So between the two, it's only gravitational interaction. So you can read that graph as a classical, something purely classical. For example, this is a classical word line in space-time. This is another word line of your object in space-time. And here you solve the Einstein equation, which you can always try to, you can try to solve the Einstein equation in perturbation, the classical Einstein equation in perturbation, by inverting the propagator of the metric fluctuations. And essentially, at the end of the day, you get some integrals, multidimensional integrals, that are just telling you how you, in Fourier mode, for example, decide to solve the Einstein equations. But one of the other interesting points is that you can read this graph as being a quantum graph, where everybody is quantized, the thick line is quantized, these curly lines are quantized, but then that when you take the classical limit, this quantized quantity exactly gives you what you want to do when you solve the classical equation of motion. So if you think about that, the starting point is to take the metric, okay, space time, and then you do a perturbation near flat space. So you think that you have two massive objects with spin in flat space-time, and then they scatter. And the thing that is non-trivial is that here, so suppose you want to look at the scattering of two Schwarzschild black holes, so that there is no spin. You can ask the question, how good is it to model this by looking at the scattering of two scalar fields? So in a sense, I mean, you have one massive scalar field, another massive scalar field. They interact gravitationally, and then as if they are point-like particles. Of course, they are not point-like because when you are in the universe, my two merging Schwarzschild black hole, they are not point-like, of course, a priori. But so the question is that is there a sense of doing that approximation? And in fact, yes. As it turns, I mean, it turns that you get exactly what the right result, at least up to the order where everything has been computed explicitly. So I've shown you this nature cover of the for loop, 5 p.m. We believe that up to 5 loop, there should be no problem. But why is this happening? So this is precisely what I will try to explain to you in this lecture. Okay, so first you consider these two massive point-like objects, okay, scalar field, coupled to gravity. Okay, gravity is here, so you do perturbation, G Newton. Okay, I didn't put the 32 pi. Okay, but this is the perturbation, and then you want to compute your quantum gravity, so your scattering amplitude, where you do have all the quantized propagator. Okay, so this is the T matrix, the matrix element, and then it gives you a perturbation in G Newton. Okay, so and what you do is that, in fact, when you do this, you treat your action. So yeah, this is the Einstein-Hilbert action. This is your scalar field. But in fact, you are really using the standard formalism of quantum field theory. That means you are using the fact that you are a quantum field theory that is local, unitary, Lorentz invariant. Okay. So that's extremely important because I said I want something that is relativistically invariant. So if I keep this statement, I mean that may be obvious. I mean because if you do quantum field theory, of course you want to keep this, but okay. But I know that I'm going to get an answer that is going to be relativistically invariant, and as well is as well comes from diffeomorphism invariants that are the symmetries of Einstein gravity. So I'm not going to miss any of the symmetries that I want to include in my computation. So here comes a very important point is that what are the degrees of freedom that I'm using? So it's extremely important to realize that. So here we have two massive objects, M1, M2. The momentum transfer here is there's very little momentum transfer. So in fact, they interact gravitationally, but the energy that is transferred here is through the massless quantity, that is particle, that is the graviton. Okay. So in a sense, I mean, you are going to be in a regime when you have a very small energy that is exchanged. And in fact, I already anticipated some of the main point of the way the computation is going to be organized is that the potential is polynomial in the mass. So essentially what's going to happen is that your quantum object here, for those of you who are somewhat familiar with something about QCD, and this is like a large mass expansion. So in a sense, you want at some point to think that the way to extract the classical um, result from this quantum amplitude is to expand your scattering amplitude as with large values of the mass M1, M2 compared to the energy that is transferred. And but what I'm saying is that, okay, by just assuming that this is a spin 2, the minimal coupling of the spin 2 to my field that is going to be the basis of my amplitude computation. So then I'm going to match what was known previously for classical GR, and then produce new result. But if you, for example, believe that there is something else, yes, there's a question. Okay, so what was the scalar field again? Yes, okay, so that's a good point. So the thing is that, okay, let me go back. I don't know which picture is the best. So, okay, so here you have two black holes. You have either two black holes or neutron stars, right? And normally, so in most of the events that I mentioned before, the black holes, they have some spin, but you can look at the question of the merging of black holes that are either Schwarzschild black holes or Kerr black holes, or as well neutron stars. So neutron stars, they are not, I mean, they have a spin, but as well they have some, the internal structure is different from a black hole, right? But the main point, which is a non-trivial fact, because this is not something that you have to believe like that, but is that when you are in the perturbative regime, which is this post-Minkowskian expansion, to some order in perturbation, you can just forget about the internal structure. So you can model your physical black holes that are, I mean, emitting your gravitational waves by fictitious massive quantum field. So if you are just happy with if you are not interested by spin, I mean, which I will do in that lecture, so that means you are just considering the gravitational waves emitted by two objects that are like two Schwarzschild black hole, then you can just model them by this massive scalar field, okay? And the way they couple. So what's only important is the way the scalar field couples to gravity. If you want then to have the spin dependence, because in this the waveform, and so you want to know how the spin of the Kerr black hole enters your gravitational observables, then of course then you have to give a spin, and then you have to compute how the spin changes. Okay, so a priori when you do the expansion. So this is the fact that up to some point, I mean, this particle description of, I'm not saying that the black holes are particles, but in that computation to the order where I'm computing, this is a good approximation. Does it answer the question? Or-
Well, I mean, it's not, thank you for that explanation, but it's not clear to me what the scalar field is. Is it one of the excited modes of the graviton, or I mean, what is it like? Where did
No, no,
the scalar
it's an
come from?
external scalar field. So this is okay. So yeah, so yeah, so this is a very crucial point. So I'm going to spend some time on it. So normally what we do is that we have two objects, right, that are interacting, and at some point they feel that the geometry is not flat space, right? Okay, but the computation is still done in perturbation around flat space. Okay. And the scalar field, they are like sources, classical sources. I mean, okay, quantum field, but at the end, when I will take the classical limit, they will be acting like classical sources in space-time that exchanges gravitational force. So this is a way to model the two black hole. I mean, are they block? I mean, they are not excitations of whatever. And the interaction, yeah, so the way they interact is by exchanging gravitons, and the gravitons are the h mu nu that is here. Okay, so so there's a minimal coupling between the space-time excitation, that is the graviton, and the stress energy tensor for each of these guys, as you derive from this action here. Does it answer the question, or?
Well, not completely, but I'll wait. Maybe it will be clarified as you go on.
Okay. Uh, so,
Sorry, I have a question too.
yes,
In the slide, in the nature image, is
yes,
that it says that it's four loops. They consider four loops in the standard
yes.
perturbation theory. But do you work with redshift of phase distortion, or you work in real space? And how do you work with bias terms? Yes, that's the question.
Work with what? So in fact, the computation is a flat space computation. Yes. So in a sense, I mean, this is really, so in fact, I mean, this picture here somewhat tells you that you have two objects that scatters, and then you can compute the scattering to some order and perturbation, so they interact gravitationally. Okay, so then you, I don't know which, maybe this one. What is this one? This one is how many loops? So it's a multi-loop version, like interaction like that, and then you compute the amplitude, and from that you extract the scattering angle, and from that you can this is the result that they have given. I mean, which is related to this. The scattering angles tells you how the trajectory of the two objects are modified by their mutual interaction, and that tells you about the way so then you can compute as well the waveform, and the waveform is exactly the waveform is so h mu nu, so yes. So h mu nu is h mu nu here. So this is the fluctuation of the metric, right? so you can compute as well to that order the waveform, and the waveform is what you fit to the signal, and that you can compare with what is detected by the interferometers. Okay. So, but I'm going to tell you exactly how to get to that computation, to what is behind this cover of nature.
Okay, thanks.
Okay, so still, okay, to try to, so in that same paper by Kovac and Thorne, they say that, for example, this paper in 78, this paper attempt the definitive treatment of the classical gravitational Bremsstrahlung. So this is the radiation of gravitational radiation produced by two stars when they fly of arbitrary relative mass, when they pass each other with a relative velocity, with arbitrary relative velocity. Okay, and so what they try to do is that they want to compute the scattering angle. Okay, and the thing is that they could not do it completely because they did not have the technique that I'm going to explain. But today this problem is solved. Okay. And now, again, to go back to this approximation I'm using about the scalar field is that it's using some kind of effective field theory treatment of general relativity using quantum scattering amplitude. And in fact, you can up to some order in perturbation, which is essentially 5 loops, forget that your black holes are, are not point-like. I mean, you can treat them as point-like object. So, and then think as if they are just this fictitious scalar field or massive field with spin if you want to do care. Okay, so this is why I'm going to need to use this this language. Is there another question? Okay, so there's okay. So there's a question. Okay, so I'm trying to read the question. In the context of perturbative gravity. Okay, right. Yes, so the thing is that this is the quantization of the fluctuation of the massless spin 2. So this is usual quantum gravity spin 2 propagating, coupling minimally to the stress energy tensor through this Lagrangian. Okay, and so this is just the question first. I mean, to do in this context of an effective field theory of quantum gravity in that case, because this is a quantum gravity. What is the potential, the interaction between two massive objects that interact gravitationally? So this is following. So then here the quantization of the graviton, I mean, is really yes, is doing a perturbative treatment. So you have two objects that interact at one loop, at 3 level, 1 loop, 2 loop, 3 loops, by purely exchanging a quantized graviton. Okay. So so this is first, you need to compute that, and then you have to connect this to the question of the classical physics, okay, which is a different question that I will have to come later. But this is really following actually the idea that this Kovacs and Fond people. So yeah, I mean, so I'm sorry. So there is of course the scalar field here is coupling to the metric, right? G mu nu, and G mu nu inverse couples to H mu nu. Okay, for this. So there's and in fact, as you realize, I mean, so here, when you derive the interaction between the scalar field and the H mu nu, which is the metric fluctuation, which is, so this guy that propagates is the H mu nu. So here, this coupling is extracted by having H mu nu multiplying the, this d mu phi, d nu phi. So this is the minimal coupling that you get imposed by diffeomorphism invariance and the symmetries of gravity. Okay, so so here the coupling between the gravitons are obtained by expanding the Ricci scalar. And as you know, because there is all this inverse metric, I mean, there are interactions to all orders. So there are some 3-point interaction, 4-point interaction, 5-point interaction, with two derivatives between the h mu. So this is why this is a very highly non-trivial expansion. But so this is the way you couple the scalar field. So what's happening is that then when you have your Hamiltonian, then there's the free part and there's the potential, which is the one I want to build. And what you can do is that you can connect this potential to a quantity that I call T. And okay, so the T matrix, the matrix element of the T matrix is the scattering amplitude I'm going to compute. Okay, so the scattering amplitude is the matrix element of the T matrix. But if you use actually the Lippmann-Schwinger equation, you can relate the scattering amplitude that you are going to compute to the object that I want to put in my Hamiltonian, which is the V, the potential V, through a set of equations that is like that. So the Lippmann-Schwinger equation tells you that normally the T matrix defined this way. So H is essentially the inverse of the Hamiltonian. Okay, so this is the free part, this is the interacting part. Is T is V potential plus some, so here I'm deciding that I'm working in free space-time dimension. So this is the potential. Okay, so the potential, yeah, I forgot to put a PM. Okay, so this is the potential. This is this potential here. Then T is the T, and then this is convoluted with this integration over this three-dimensional vector, which has to do with actually the energy of the that is exchanged for the states that are propagating, that are inserted here. And because it's a perturbative expansion, that means G is small, and then V has a small G expansion, which I already have presented to you in powers of G to the L plus 1, you can invert that expression. But you see, when you invert it, you realize that actually this V is T, okay, minus, okay, because there's a plus, and then there is TT, there was VT, there is TT, but then there's dot, dot, dot. So that means there's an infinite series of terms with more and more T's and more integrations. And essentially, this is where you are going to get all the perturbative computation. So that means if you want to get V to some order in G Newton, you will have to compute these multi-integrals, to higher orders, knowing that actually the T is related to your amplitude for this. Okay. So let me be concrete and see how it works for the simple case. So here you have a scalar field of mass m1 and a momentum p1. Here you have a scalar field of momentum p2, mass m2. And they just exchange one graviton. Okay, so this is the coupling. So this coupling is exactly what you get from here. So that means here G mu nu, you replace it with H mu nu, and you have d mu phi 1, d mu phi 2, d mu phi 2. Okay, so that gives you the vertex here, that is going to be the of order p square, and then coupled to here the h mu nu here. So then there is p2 square from the vertex here, and then there's the propagator, 1 over q square, and then the propagator of the graviton. If you do compute this, and if you call q to be the momentum transfer, then you find that this amplitude is proportional to G Newton. Okay, so it's because here you see I have my perturbation of the metric is flat space plus square root of G times H. Okay, so since I have two vertices, one as a square root of G, one as a square root of G, so the total is of order G. And then the vertices are two derivative order. So that means it's order four momenta. So this is because it's two derivatives, so there is p square and p square here. So this is p to the fourth. Okay. And so if you massage it and you can organize it this way, and then what you do is that instead of using q, normally you would, if you look in the quantum field theory book, you see 1 over q square is the propagator. So instead of calling Q square, I call it Q I call Q to be H bar Q underline. Okay. Then if you do this way, then you realize that your tree level amplitude takes this form, which is, so here I'm doing nothing, I'm just expanding. There's 1 over H bar pole, which has for the residue this piece, okay? And then there's a piece where the Q square is cancelled, that is proportional to H bar, is proportional to P1 dot P2. So this one grows, I mean, it's something that grows like the energy. So this is actually the fact that at high energy, the theory is not renormalizable. So you have the contact term, so the short distance behavior. And then there's this piece, which is, when you look at it, you take that piece, and then you go back to position space, you Fourier transform to 3 dimension. So you normalize your integral correctly. And then you exactly get what I said, which is Newton's potential. So the relativistic version of Newton's potential. So this factor of gamma is just rewriting of this factor here. So in fact, this thing is telling you one thing, is that the classical Newton's potential, so relativistic invariant, is coming from, of course, a tree level graph. So tree level has to do something with what you call Newton's potential. But in fact, when you look at it, your quantum amplitude has 2 pieces. One that goes like 1 over H bar, one that goes like H bar to the H bar. So if I take H bar going to 0, that means I say, okay, I want something that is purely classical. I take H bar going to 0. Well, this object blows up. So because there is the 1 over H bar, okay, so in fact, I mean, what's going to happen is that all the terms in the quantum amplitude that are the classical piece are the 1 over H bar piece, okay? But as well, what you call tree level is not purely classical. I mean, it has what I call a quantum piece. This thing has nothing to do with pure Einstein gravity. You don't put it in what you call a classical observable. It has to do with the fact that you have a short distance behavior at high energy in quantum gravity, okay? So now if you do that, suppose now instead of looking at something that is one graviton exchange, you look at something that is a scalar field, and then this is a graviton. So just focus on that piece, okay? It's a local analysis. So this is the graviton, and then the graviton emits another graviton, okay? So it's just one scalar field. So locally, an amplitude that has this factor will have a propagator. So this is this piece. Okay, so this piece in the middle, okay, let me say it differently. This piece in the middle is the massive propagator. This one and these ones, they are the massless propagators. So what's happening is that normally you have a scalar field of mass m that propagates here, okay? So normally you have L square minus m square. But if you get back to put C and H bar, so that means you don't use C equal 1 and H bar equal 1 as we normally always do, then you realize that actually the Klein-Gordon equation is there is this inverse quantum wavelength, m square C square divided by H bar square. So that means when you do the small H bar expansion of that triangle, this term can become very big. And in fact, if you do that properly, then you realize that the behavior of that integral when H bar goes to 0 has a term that is MC divided by H bar, again, a pole in H bar, square root of Q square, plus a piece that is the log that has no H bar, Q square divided by, the Dimrek scale. And in fact, the interpretation of that, if you then Fourier transform this in 3 dimensions, okay, the same way, you find that this term is 1 over r square. So this is 1 over r square times g Newton square. So that means it corresponds to the next order correction to Newton's potential. So, okay, so this is precisely what you want. And this term is something that you don't want in classical theory because it has to do with quantum physics. So the statement to all order is the following. So now if I take this a graph like that, many loops, okay, purely gravitons, all the Feynman rules derive from this action, okay, with the gauge fixing and whatever. And I then do what I said is that I decide that to scale my momentum transfer Q to be h bar Q. So, and then I take h bar to 0, and then I have a small energy. So the energy that is transferred is small compared to the mass of the object. My amplitude will have an expansion that is like that. There is a piece that will be 1 over h bar times something. And by dimension analysis, you realize that, okay, if you take d equal 4, yeah, this is exactly what you want. So when you will be at L loop, the power of the Newton's constant will be GL plus 1 by construction because you are L loop. And the power of Q underline square will be exactly what you need so that when you Fourier transform to 3 dimension gives you exactly the right power of R to be L plus 1. So dimensionally, you are happy that, okay, so I didn't write explicitly the power of G Newton here, but this is exactly what you want. So in a minute, I will comment on the factor here. But, okay, so as we say that tree level L equal 1 loop, so there is something more, of course. So there is 1 over h bar. So L equals 0, I'm sorry, the tree level L equals 0, there is 1 over h bar, plus there is this h bar term. So the triangle was L equal 1. So there was one term that was 1 over h bar plus the log, okay? So in a sense, I mean, this is an expansion where I have a lot of terms that have positive powers of h bar. They are all of quantum nature. So they have to do with the UV physics and things like that. So this one I don't care. But the thing that is a bit disturbing is that, okay, so you can say, you can try to think about a rule saying, okay, so it has 1 over h bar, but if I just look at the term 1 over h bar, maybe I get the right result for classical gravity, okay, which is what you want to say. But then you realize that your full quantum amplitude has terms that each time you increase in loop has more inverse power of h bar. And I'm going to explain to you why this is happening and why it should happen, okay? But the statement is that you have here in that context, so normally you think that when you do a perturbation in quantum field theory, L loop amplitude has a factor that is h bar to the L minus 1, okay? And that's, I mean, this is, I'm not saying this is wrong. I mean, this is of course correct as a generic statement. But when you have massive external particle and if you do an expansion that is such that these external particles are very massive compared to the energy that is exchanged in your scattering amplitude, then you have to reorganize the way the loop expansion is done with respect to this massive object, because this massive object, the mass actually comes with 1 over h bar in quantum physics, okay? So in a sense, I mean, if you have something like that is a graph like that, okay, at L loop, it will have h bar to the L minus 1 as usual. But then if you want to extract something that is of given order in the mass of the external particle, because the mass M1 and M2 are very big compared to the energy, then you will pick some specific powers of M1 and M2, but M1 and M2, they will come with this one inverse power of h bar. And so they will compensate for the h bar to the loop minus 1 that was in front of your amplitude. So that means some of the term will be such that there will be a lot of 1 over h bar from this mass expansion. This is these guys. And essentially, you have a maximum number that is dictated by dimension analysis and up to terms that are regular, that have no inverse power of h bar. And what I said is that because the potential you want in classical GR have a very specific dimension in terms of the mass, so you need something that depends on M1 and M2 so that the total degree is fixed, I mean, connected to the loop order, then you realize that essentially by dimension analysis, the term you want is this one, not this one. But in fact, the other terms, I mean, they can arise as well if you have higher powers of the masses and that are not associated with the potential that GR instruct you to keep. Okay, so this is one first way to somewhat realize that actually getting 1 over h bar terms is not so bizarre if you do a large mass expansion in quantum field theory. Okay, and what I'm saying will apply as well if you study QED. So that means you have an electron that interact an electron and a muon that are very massive compared to the energy that they interact, and then you just do an expansion in terms of the masses of this charged particle. So it will be the same. The other point, which is actually extremely important in that computation, is that this is a classical gravity computation. So there is no question about UV divergences. It's not a question of quantum gravity, although I'm using quantum gravity to do that. But the piece I want to extract are not affected by the quantum gravity non-renormalization issue. They are in the OER, they depend on h bar with higher orders in h bar, so they are in that piece that are polynomial. But still, I have the question of infrared divergences. So the fact is that classically, even for classical field, you have the fact that you have your massless field that propagates over long distances, and then you have to treat the question of these infrared divergences that are classical infrared divergences. But in the respect of this quantum scattering amplitude framework, these infrared divergences are treated the same way that you treat infrared divergences, I mean, in quantum field theory. So if I do dim-reg, this is why I'm using dimensional regularization, then I need to keep track of this 4 minus d, which would be a way to correctly control the infrared divergences from the gravitational radiation. Okay, so now, I mean, I want to build my Hamiltonian, so I need to go to this potential, which I call this VPM, potential post-Minkowskian expansion, which from the Lippmann-Schwinger equation is connected to the scattering amplitude through the T matrix element, okay? So the T matrix element are the one that normally you know when you have the scattering matrix X, S, that yes, that's exactly this. Yes, that's correct. Yes. So, okay. So, yeah. So no, I have described something about this scattering of this scalar field and the S matrix. So the S matrix is the identity matrix and the scattering matrix. So this is what you see in quantum field theory. Okay. So T here. T. So the vacuum expectation values of T's give you M, okay? So in essentially, T to some order in perturbation, so this T here, gives me this M, from which I want to extract the 1 over h bar here, okay? And then from the M I get the T, from the T I get the V, and from the V I get the Hamiltonian, okay? So this is a bit of a... So the thing is that, okay, so tree level, I showed you this is easy to extract the coefficient. So one loop you already have, okay, it's a little more complicated computation to do one loop, okay, but you can still do it with pen and paper. Then you get L equal 1, so you'll get something that go like 1 over h bar square, and then 1 over h bar plus something, and then you realize that the higher you go in perturbation, 2 loop, 3 loop, so you get a lot of these terms that are polluting your computation, and you want to extract the 1 over h bar. And honestly, as you can guess, doing this, we are doing a computation in pure gravity, right? So this is massively difficult in terms of the tensorial structure. So in fact, it's better to try to get a result that is such that you don't have to subtract something, and you just get the piece that you can use for your classical result after you have properly normalized by taking a limit. And as well, the question is that, okay, I told you that this thing has to do with this large mass expansion, but okay, so maybe there's a better way to understand as well why there is this 1 over h bar expansion. Okay, so normally what happens is that the T matrix that you have has an expansion in terms of your coupling constant, which is G Newton. So of course, tree level L equals 0. This is T0, so there is always, this is G Newton because and then one loop is G squared, okay? And then there is a piece that is there called radiation, which has to do with, okay, suppose I could have a graviton that is emitted from an external line, okay? So I could have here something that is 1, 2, they interact, and then I emit as well a graviton from here, or from here, okay, or from here. Okay, so that means I would have, instead of a 2 to 2, two particles, those two particles, I could have the two scalar field plus emitted one graviton or two graviton. Okay, so this is the emission of graviton in the external state. And so what I decided to do is to say, okay, I ask what if I write the S matrix as an exponential? I n hat over h bar. So n, of course, has an expansion in the conservative sector. That means no external graviton in the in or out states. And here there are gravitons in the in or out states. Okay. And of course, as well, when you do S matrix, so S is unitary, so S dagger is 1. And the completeness relation tells you what exactly what you are doing. So the sense is that you are working in a phase space where you have two massive particles, my two massive fields. Okay, so this is the integration of and then they are on shell. So particle 1 has mass m1, particle 2 has mass m2. So and delta plus means delta function. So the 4-dimensional delta function with positive energy. Okay, so this is the on shell condition. And then this is the graviton. Okay, so I have a sector that n equals 0, where I have no gravitons, and then I have n equal 1, 1 graviton, 2 graviton, etc. So I'm integrating over all the possible gravitons, their energy. So this is the properly normalized phase space integral, and then this is the states. Okay, and so this is exactly the completeness relation that ensure that in my context of this computation, S dagger is 1 and this one. Okay. So now I look at what is the relation between n and t. Okay. So I have the first order n0 equals 0, n0 rad equal t0 rad, and then I see by taking the log. Okay, so that n1 is t1 minus 1 over h bar t0 square. Okay, the radiation, and then n2 I have t2 1 over h bar t0 square, t0 rad square, this one 1 over h bar square, t0 cube. Okay, so let's try to see what's happening. So I have an in state that is particle 1, particle 2, momentum p1, momentum p2. They have interacted, they get out. their momentum have changed. So P1 is P1 prime, P2 is P2 prime. Okay, so this relation tells me that N0 is T0. So at tree level, nothing happens. Here, because I don't have any graviton in the either in the external states or internal in states, I mean, this is 0 by definition. And now let's look at one loop. So I'm getting this is equal to this minus this. Okay. So this expression here is the amplitude that you would compute if you compute a one loop amplitude. Okay, so yeah, let me see here. So you would just compute this amplitude with just one loop. So for example, okay, forget about that part, just focus on that part. Okay, here, for example, this is one graph that will come at one loop. Okay, so see just one loop here. So if I just but there's as well the case where there are the lines that are parallel and things like that. So this is all the one loop amplitude that you compute by exchanging gravitons between your two massive objects. Here, this guy here, it comes from T0 square. T0 is the tree level amplitude. So each of the T0 is this. So this is what I call T0, but you have to rotate it by 90 degrees. Okay, so this is just one graviton exchange. Okay, so this is the guy, one graviton, the guy, one graviton, and because I've inserted the completeness relation here, I'm integrating over the momentum here of the particle that goes between my two trees. And because here I have this delta function, I have to remember that I have the delta plus function insertion from the completeness relation. Okay? So now what is this? This piece is what I call the one loop amplitude I compute. So this is this. And then I find that for a computation that it has something that is 1 over h bar square times some power of what I call underline q, something that is 1 over h bar plus something that is of order h bar and things like that. So this piece here, the 1 over h bar piece, actually you see, when you do the computation, you put all the factors of I and 2 h bar and do it carefully. What you find is that actually this quantity, that is this minus this, oops, I'm sorry, is exactly just the classical piece. So that means the 1 over h bar square here are just cancelled. And in fact, n is given by just this piece here. So there is no h bar here because I have here, put the h bar here. Okay, so in the exponential, I have I n hat over h bar in the same way that I have I t over h bar. So this is normally so that this guy starts as something that is of order 0 in h bar plus correction in h bar. So in fact, what's happening is that the relation between n and t, the 1 over h bar square is cancelled. And this piece, which is the sum of two trees, you see, is the fact that this is the unitarity, the fact that in the one loop computation, there is always by unitarity the iteration of the lowest loop order. So for example, the trees, and because I'm at one loop, so I have actually two contributions of tree level contribution that are included into the full quantum one loop amplitude. But the relation between n and t precisely cancels this thing that is imposed to you by unitarity from that comes from the lowest orders. Now, if I go to higher loops, then this is why I see why I had to introduce, because so far, I mean, in that lecture, I only want to discuss the conservative part. So that means 2 to 2, so my 2 black holes comes and 2 black holes get out. So, but I don't want to include actually observables that have graviton in the external states. But I do need them in my computation, because if I do here something that is at, so you see this is 3 levels, but this is 1 loop, 2 loop, 3 loop. So this is a 3 loop contribution, and unitarity forces you that when you properly look at the relation between n and t, okay, so here, for example, you see that n2 that has no radiation is related to, oh, okay, so this one should not have radiation, but this one has radiation. Okay, so this one should not. Has to contain in the subgraph pieces that actually here, when you look at it from the perspective of this isolated graph, is something that contains a radiation. Okay, but okay, once this is imposed on you on just the fact that you are rewriting the element of the S matrix using this exponentiation. So why do I do that? I do that because there is this notion of what you call iconal approximation. That is a way that that is used, I mean, in optics, but as well in quantum field theory, when you realize that you can resum. For example, in QED, you have your electron that interact, I mean, by exchanging photons, and they exchange lines of photons, and the line then can cross. And when you sum all these graphs to all order, then you realize that this is an exponentiation of just the single photon exchange. So in fact, it's natural when you sum many orders in perturbation in quantum field theory to have an exponentiation of some graph, because this exponentiation gives you a quantity which tells you, which then is related to the scattering, the way for example, if you have your 2 electrons that interact by exchanging a photon, then you can compute the scattering angle. So this is what then gives you the way to compute the scattering angle. So the problem is that guessing a way for doing this iconal generalization of the iconal approximation in quantum field theory is not an easy question, and it has been looked at for a long time. But it turns that we have proposed this formulation that looks, at the end, when you explain it, it looks very simple, but okay. So, but that's the proper way to define the way you extract this classical this quantity, that is such that when you then take the h bar going to 0 limit of this n, so n1, n2, so to all order and perturbation, you will get exactly what you need to put into your potential, classical potential for your post-Minkowskian Hamiltonian. Okay, so this is what I said. So the fact is that the result of this analysis is that we have a way to exactly do what Forn and Kovacs were saying, in a sense of trying to find a way to use the Feynman integral. So this is using Feynman integrals. This is all this thing is computed using Feynman integrals here, and compute actually quantities that are going into the S matrix, classical S matrix quantities. Okay. So I have no idea about, yes, okay, the time. Okay, so you tell me when I should stop, right? So okay, so let me summarize. The thing is that, so you can compute a scattering amplitude. Okay, so in this scalar field description, you build from it this n operator, which is built from your scattering amplitude minus the thing that you get from lowest order graphs. So using this relation between n and t, so which is taking the log of your S matrix if you want. And then the way it's properly normalized, this n operator, is that when it starts really by something classical plus quantum corrections. Okay, so at this level, here no information has been lost. Okay, so in a sense, I mean, okay, so if you want to do gravitational wave physics, you take h bar going to 0 limit of this, you keep that, and then you throw away this. But I want to tell you that if you are interested about something that is beyond Einstein gravity, okay, so suppose you want to have that your black hole, they interact not just with massless graviton, but suppose you imagine that exists another massless field that we haven't seen yet, that can interact with your black holes. Of course, you can include them because it's so if you know the interaction in your Lagrangian, you can compute the scattering amplitude, right? So that means you will compute the new modified scattering amplitude that normally you could feed into your classical post-Minkowskian potential and see how it fits better or worse the gravitational wave data, okay? So in fact, what I'm saying to you is that this is really a formalism that puts Einstein gravity in the context of an effective field theory, right? So either you decide that, so this is what I was saying at the beginning. So in a sense, I mean, the gravitational wave signal, they potentially contain informations about what is beyond Einstein gravity in our universe. So if this is the existence of extra degrees of freedom that can affect the way gravity propagates, I mean, this is a way to put it in the formalism. If you think as well that there is some extra dimension, so as well you can compute the amplitude and extract how it changes the form of your scattering amplitude in 4 dimensions, right? So this is so this is for the classical bit. So if you're interested about quantum corrections, and at the end of the lecture maybe I will say something about that, but then you as well have the way quantum correction modify the classical Einstein gravity result. So at this level, nothing is lost. So this is really what I wanted to insist on that. So now let me recap. So the S matrix, instead of I plus 1 plus I over h bar t, is exponential I n over h bar. And now I'm just focusing on the classical bit, so which is the one I've extracted for the procedure. So gamma is the relativistic factor, and q square is the momentum transfer. Okay, so I Fourier transform n. Okay, so and then instead of using the impact parameter, I use the angular momentum j. Okay, so there is instead of having b times q, I'm using j over p infinity, and p infinity is some quantity that people in classical GR they use. And then you find that from the tree-level amplitude, this is what I told you about Newton's potential, at one loop, which is the first general relativity correction to Newton's potential, you get something that is of that form. So you see this is symmetric M1, M2. This is depending on the mass M1 plus M2. This is the total energy. And then there is still the relativistic factor. Okay. So these two quantities, n, actually you can find them in a book about general relativity. And you realize that they are, I mean, in fact, this is, in fact, in Landau-Lifshitz. And when you look at the test particle evolution in a Schwarzschild black hole, so this is, instead of having two objects of mass M1, M2, you can reduce it to a system when you have a big black hole of mass M1, M2, M1 plus M2, and a test particle in it. And then you can try to compute what are the geodesic and the equation of motion, and then you find that this is exactly giving what I've computed here for the potential. So the thing is that, so that says one thing. So it says that at one loop, tree level and one loop, we have a validation of the method, which is non-trivial because from the start, I mean, you could have asked, I mean, why is this quantum method going to give you anything that is relevant for this classical gravity question? So this is a validation of the method, and when we did that computation, it was not for getting new results, it's to make sure that we do things right. Now, the thing that is interesting is that, the two-loop computation, which is 3 p.m., so 3 p.m. in g Newton to the cube, it's a two-loop computation. Now is a new result. So the thing is that there were some results in classical GR, but I mean, most of it, what is on this slide, is really the place where this scattering amplitude method started to produce new result to the GR community. And it has been done by many people, like me with Émile Biombor, Paul Damgard, Ludovic Planté, but as well as Vibern and Julio Parra Martinez and company, and as well the group of Gabriele Veneziano, Jorge Rousseau, Carlo Eisenberg, Paolo Di Vecchia, and as well Thibaut Damour. So there's many people who contributed to that, and it was important to make sure that what we are doing is the right thing. I mean, in a sense, I mean, it's I want to tell you that it is a non-trivial conceptual reformulation. So we had to check that what we are doing is right. So, no, we believe that, but it's not because so there have been a lot of cross-check. So if you look at what happens from two-loop graph, then you realize that this order, the result is very interesting. So first, you already see that there is no, so there is no structure like M1 plus M2 that is obvious here. Okay, so in a sense, I mean, you start seeing that it deviates. So it's not anymore. So this part. So I call that conservative, and there is a part that is called radiation reaction term. So this part that is radiation reaction is the part when you have a graviton that propagates inside the loop. Okay. I will explain to you in a minute why I split that this way. But when you look at this result, then you see it's not anymore the one of a test particle in a big black hole. So from two loop, which is 3 p.m., your two objects that interact, they start to feel that the space-time is modified by the presence of the other one. So it's an interesting computation that actually shows you that the probe, so the probe particle computation is not anymore a valid computation. Okay, so that captures something that goes beyond. So in fact, I mean, this is not something you could find, for example, in the book like Landau-Lifshitz, because Landau-Lifshitz only does the test particle approximation. So at this order g Newton to the cube, you will not see such intricate expression. Then you start seeing object that has this arcoche of gamma. So you start seeing functions that are more completed than square roots. There are some logs. And in fact, as I said, because you are fully relativistically invariant, it's of course valid from the static case, which is gamma equal 1, to ultra-relativistic regime. Okay, so that means when the speed of the two objects is close to, the relative speed is close to the speed of light. So that means gamma going to infinity. So if you go to the limit gamma to infinity of that computation, there is a nice, interesting cancellation between logs in this expression here. And in fact, this is a check that actually in this disorder and perturbation, there's the fact that when you go to high order and perturbation in G Newton, there is the so when you have particle 1 that interacts with black hole 1 that interacts with black hole 2, in fact, there is the fact that some graviton can travel from previous order. So in fact, there is this propagation of the graviton that hits you back, and this is related to what people call radiation reaction terms, okay, which are infrared effects, because these graviton, they propagate to long distance. And if you don't include them correctly, you will not be able to reproduce this high energy behavior correctly. And in fact, I mean, it's a very, very, very nice and strong confirmation that these techniques of computing the amplitude the way I've described, using scattering amplitude, taking this classical limit, and using dim-reg to control the infrared divergences that you have when you're in your amplitude because you have massless particle propagating, everything gets the right answer. Okay, so now once you know equipped with an amplitude technique, then you can define in generic way. So far I explained to you compute an amplitude, but suppose you have an operator O and you want to compute what is the classical variation of that operator. So Kemok, Kosovar, maybe O'Connell, they told you that if you have O, like the momentum kick, so the variation of P1 prime minus P1 of, for example, one black hole, or the change of the angular momentum, whatever. So suppose you want to compute how this thing changes classically in your scattering process. So the procedure to do that is built from everything I've told you. So you take your observable in the in states, so the way it is at the beginning before scattering, the way it is in the out states after scattering, and you call it delta, the difference. Okay, so far it's not very, so this is an obvious definition, but what these people explain to you is that this delta takes the form of this integral over q, which is the momentum transfer, of here a very precise delta function and the Fourier transform. And this element here is computing using the S matrix method familiar from quantum field theory. So here you see something that is interesting is that the delta function here that you have with the h bar, when you take h bar going to zero limit, okay, you see this term is going to be subleading, this term is going to be subleading, as precisely, I'm sorry, the form here, which is like that, okay, because if you expand this, you see that there's an h, so p1 square is m1 square, so there is h bar p1q, and there's h bar square q square, which is exactly what you have here. So this delta function that you get from the Kemok prescription, which is motivated without using what I just said before with the completeness relation. I mean, it's the way you build the wave packet and go from the momentum space to the direct space, is exactly aligned with this prescription I've told you to go from the scattering amplitude to the classical result. So this is why actually the Kemok prescription from the variation of this classical quantity, delta O. Okay, so if you use that, out is S matrix acting on in. Okay, so out O out is in S dagger O hat S in. Okay, minus this term, so you can write it this way. And then if you use that S is exponential in over h bar, then you get a nested expression with commutators. So that means no, I've told you how to compute one. So I've presented a method here to compute one case, but in fact it's not more complicated to apply it to the case where you have a commutator and nested commutator, and what I've said before applies. So then there is the limit of this quantum. So this is computed in a quantum formalism. So there is h bar everywhere. But if you then take the limit, h bar going to 0, because there is the n operator that has the property I just presented, you know that actually the limit h bar going to 0 of this is going to be well behaved, give you the classical result, that's exactly what you want, plus quantum corrections. So if you, I just want to make another point, is that if you use the t operator instead of the n operator, you will have the problem that at each order you will have this 1 over h bar powers that you need to cancel, that you know they are canceling, but it's complicated to show they cancel. This thing gives it to you. Okay. So now, what you can do with that. Okay, so suppose you want to look at the momentum kick. So that means you want to see how the momentum of one of the black hole changes through the gravitational interaction with the other black hole. So in fact, it's a computation. You can do that. Actually, you can. It's simple enough so that you can resum to all order, and you get an expression that is like that. Okay, so delta P1, it's a vector. It depends on the relative distance between the vectors. The P infinity already introduced before. And L is the angular momentum. Okay, so L satisfies that L square P square is 1. Okay, so, and then there is something that, okay, so here you have the N operator. So you compute the S matrix element. Okay, so then I do the Fourier transform with respect to J. And at the end of the day, the result gives you that you can resum everything to sinus of something that involves the derivative with respect to J of the N operator and the cosine. Okay, so it's the result of the computation of the amplitude using this when O is P1. So now let me compare to what you have when you do classical mechanics. So in classical mechanics, what you do is that you have the impact parameter B, and you have, for example, let's say suppose you are in the center of frame of one of the two massive objects, the other one comes, interacts, and flies, okay? So then what's happening is that there is a deflection angle, yeah, depending the way you define it, but theta or how you call this way or this way. So, so there is the Hamiltonian. So this is the same as what I said before. And what happens is that then you can write the Hamiltonian in spherical coordinate, okay, because it's a central potential. Okay, so P square is P radial square plus angular momentum divided by R square, and P square is so there is a theta and there is pi. So it's just going to spherical coordinate. And then if you look in, for example, the book by Landau and Lifshitz, you see that there is the Hamilton-Jacobi equations for the radial contribution that is given by a derivative with respect to R, a quantity that's called S, the part that has to do with the angular momentum, the potential here that was already spherically invariant that doesn't depend on theta, and this is equal to the energy. Okay, so this is solving the Hamiltonian. Okay, so the S that you get from the book, like classical mechanic book about this, the way to rewrite the Hamiltonian-Jacobi equation in terms of this S quantity. S is related to J times theta. Theta is the scattering angle, okay, plus a quantity I call N. N is obtained by the energy minus the potential minus the angular momentum part. So this is something, and then from this, because S is a conserved quantity with respect to J, then you deduce that theta is minus, because ds over dj equals 0, then you deduce that theta is minus dn over dj, is given by this. Okay? So you use that formalism to compute as well delta P1, so P1 is this and delta P1, Okay, you have to change frame because I'm not in the same frame. And then you realize that actually you get that formula here. So that formula that is derived by computing the scattering amplitude and taking a classical limit is exactly reproducing what you get from solving this classical mechanic computation of calculating the deflection angle or the momentum kick in a central potential. So you can do that without saying what is V, as long as you know that V is slightly invariant. Okay. So this is, then you have the relation between theta and dn, and then that means you know that you have correctly identified what I call the n hat, which is a quantum quantity operator. That means this vacuum expectation value gives what we call the radial action. I mean, what is called the radial action, it's not me, on the olive sheets, and you can look as well at Thibaut Damour, the way he used it. And then this way, we know that the scattering angle is obtained by the derivative respect to j of this function. I've presented the form of this function to some small order and perturbation, and then which has an expansion in terms of g Newton, the mass, and the angular momentum to some loop order times some pieces. Okay. So this is the way. This is exactly what you have, for example, on this cover of Nature. Is that cover of Nature? Okay, maybe I will go down. Yes, it's maybe I should have. Yeah, somebody on the chat. Okay. So I don't see the what is the message? Oh, okay. So right. So this cover on Nature tells you about the scattering angle, and this is exactly what you compute, but to some higher order than what I have presented. Right. Okay. So this is exactly this. So this is like, so if you fix one particle, you see one particle as kicked, the momentum as kicked, and then you can compute delta P1, you can compute the scattering angle. Okay. Okay. So this is one piece. Okay. So now in the time that I'm left, okay, I will. So I understand that there's no break, right? Okay. There's no. Okay, so now I will move to something that is again in the line of connecting this quantum scattering amplitude to classical GR. So I want to see how I can understand. So I have been using massive point-like particle to model, to compute the observable associated with the scattering of real black holes, okay? But so far, I haven't seen the black holes, okay? The scalar field were like a trick of computation. So now we are really talking about objects that are black holes in Kerr space. So in fact, I mean, so this is an interesting question, is that where are these black holes? I mean, where do I see really the metric of the black hole? So how is it possible with this approach for scattering amplitude to exactly understand how the space is curved? Okay. So still, from 72, yes, Mike Duff asked the question is that, okay, we have some theory of quantum gravity, but you know, when we have a quantum theory of quantum gravity, it would be good to test at least if we get the correct classical limit. So here's the question. I mean, how does the Einstein's equation arises from the appropriate h bar going to zero limit of a quantum gravity setup? So in fact, he was not really using the formalism I described to you, but this is a generic question, is that when you know that you pretend that you have quantized a classical system, you want to make sure that you can go back from the quantum system to the classical system, right? So let's see now how I get a black hole metric in the way I work. So the problem is that getting a black hole metric it's something that is non-perturbative, right? Because you cannot describe your curve background by just working at some fixed order and perturbation. You have to sum an infinite number of perturbative contribution, an infinite number of G Newton of contributions. Okay, let's try it. So I already said it, but I'm repeating. So the thing is that if you want, so if you want to describe a Schwarzschild black hole, that means you just need a massive scalar field. That was what was asked in the question, but has no spin. If you want to compute a Reiser-Nordstrom black hole, you just need to put an electric charge. And if you want a Kerr-Newman black hole, you need both a spin. You need a spin and a charge. So that means you have to, it's not enough to work with just scalar massive field, but you have to work with, for example, fermionic field or some spin, okay, some higher spin if you want. So to compute the metric, what you do is that you don't compute, you should not compute just an amplitude between 2 to 2, but then you compute the emission of a graviton, because the metric, you want to reconstruct the h mu nu in the perturbation that I have presented to you. So that means you want to extract what is so here are the loop corrections, an object that have your massive object that emits one graviton. And then you want from that to extract something that has to do with the waveform, the h mu nu. So the h mu nu of the metric perturbation is obtained by computing this form factor, which is organized in perturbation, and each order in G Newton. Then you Fourier transform using a formula like that, and then you get h mu nu. So first you have to understand one thing, which is extremely, because this is a very interesting point, which is not very well known. So when you do the scattering amplitude computation, you do perturbation near flat space. So you remember I had eta mu nu plus square root of g h mu nu, okay? So that means the gauge fixing term that you are going to do are in what is called the Dedonder gauge, okay? Which is eta mu nu times the Christoffel. So, or if you want, eta mu nu times this is the metric, okay? And in fact, what's happening is that if you look at the metric for Schwarzschild in the Dedonder gauge, it takes a form that is very different from the one that you are used to in the harmonic gauge. So in fact, it's spherically symmetric, so you have not lost that. So there is the time component, there is the radial component, and then there is the angular part. But you see there is some function. So it's a function of the Schwarzschild radius. So if I'm writing it in d dimension because I want to get the Schwarzschild black hole in 4, 5, 6 dimension. But so and little d. So when I am in 4 dimension, little d is 3. So this is g. So d, little d is the number of space dimension. So if I am in 4 space-time dimension, little d is 3. So this is the standard 2gm over r factor. But you see there is a function here that is strange because it has an infinite series expansion. It has to do with the fact that you are not imposing g mu nu gamma lambda mu nu g equals 0, but eta mu nu, which is a very different gauge from the one that is the harmonic gauge. Okay, so what you do is that first you have your massive field that emits one graviton, so that gives you something proportional to that. Your massive field interacts like that, emits one graviton, but after having a graviton interaction. So I follow the rules I explained to you. I compute this triangle graph. I've put all the vertices I need. Then I have I take my n operator that imposes that there is a delta function on my integration over the loop momentum. Okay, so it's 2 loops here, so 3 loops. So this delta function here, that is as well the one that you get from KMOC, kind of freeze each of the massive field here. So this is like map to computing tree-level graphs. So this is a more familiar expansion that you get from classical GR, that you have one mass in space-time that radiates a graviton. Then the mass moves, so the mass is fixed in space but moves in time. There's an interaction, gravitational interaction between your source. It's self-interaction actually, because it's different time but same position in space. So it's self-interaction that emits a graviton. So this is more self-interactions. So okay, so this is this mapped to this. Okay. So you do that. Okay, then you can compute. Then you find that there is some integrals. Everything is nice because the integral you have to compute are simple. And then you find this. So you find that from this amplitude computation in perturbation, you find that the time component of your metric is 1 minus 2gm over r. Okay, so if you are in 4 dimension, okay, that you are happy with. Then you get this one. You're happy because this is the expansion, the first order expansion of the standard factor you want for the Schwarzschild metric in 4 dimension. Okay, but then you go to higher order, and then you find a log. What is this? And then you look at the H1 term here. And then you realize that, okay, at this order, then you find a log. And then there's a log. And now, so this is coming from computing this form factors using the rules I explained and performing that. Okay, so you check the computation and you say, okay, you cannot find no mistakes. And then you realize that this is what I said, is that the amplitude computation is done in the flat, in this Dodonder gauge. This is eta mu g mu nu. So in fact, there is some residual symmetries that is left over. So you don't fix everything. So there is the possibility of doing some redefinition of the coordinate system. So that means when you compare, this is what I'm saying. So when you compare your amplitude result that is done by having expanded near flat space, you realize that there is you haven't fixed all the freedom in writing your metric. So there's still a possibility of changing x, the special part, by multiplying by a function of r. And this function can depend on g Newton. So that means it's changed to all orders. It's precisely changed to all orders because you see, if you impose the harmonic gauge condition, g mu nu is the inverse of this, right? So that means when you compute this and you multiply by this, you get an infinite series of terms in g Newton, okay, coming from here. But you don't have them here because you have just truncated it. So this is, you have to compensate by doing this transformation that order by order and perturbation reabsorbs the term. And in fact, if you have never read it, I advise you to read that paper by from Holmes, Eric Poisson, and Clifford Will, that with the title "The Schwarzschild Metric." It's the coordinate stupid. That I give the reference here. It exactly explains to you that depending on the way there's a way to solve, Schwarzschild metric in a form that you don't even recognize that is Schwarzschild metric, but it's totally equivalent. It's a different choice of gauge. So this is why amplitude people like to do this, but then, this is not good because you are in the wrong coordinate system, and as well, I have not been able to do an all-order computation. So we went to some g Newton to the fourth with my student, but in fact, it's very difficult to tell what is the term of g Newton to the 100. So we cannot claim to have recovered the full spacetime metric for this perturbative computation because we haven't done a computation to all orders, right? Okay, but now, since there is this complication by doing this Dodonder flat space computation, and the people actually, if you look at the book written by Eric Poisson and Clifford Will, you see that people doing general relativity, post-Minkowskian, post-Newtonian expansion, they use that harmonic gauge in this form. So this is the derivative of an object that is called the inverse Gothic metric that actually is discussed by Landau and Lifshitz in their book. Then you realize that maybe there is a better way to do this. So this is what I'm going to do in the last time that is left. So I want to know, so what I've been telling you that the potential is an expansion in G Newton and polynomial in the mass. So in fact, if you have one mass that is very small compared to the other one, okay, like this, then you can organize. Okay, so there's a. Oh, okay, so there's a question. What does it mean to choose the correct gauge here, having an infinite result? No, okay, yes, that's an excellent question. Okay, so I'm going to answer that. There is no bad gauge, right? So yes, the name incorrect gauge is not right. So you can work in any gauge you want, right? You have the gauge fixing as soon as you do everything correctly. So that means, in a sense, you choose a gauge, you gauge fix your action, you introduce your gauge fixing term, you have the associated ghost, and then you do your computation. So the problem is that, as I said, this is okay. So this is the natural, I would say, I should have said that. So, yeah, this is a natural gauge when you solve classical Einstein's equations. So you take your favorite book about general relativity. When they present, for example, Weinberg, when they present the solution to Schwarzschild metric, they would work in this gauge, right? But if you try, for example, to write the Schwarzschild metric in that gauge, then you will have an expression which will involve this function f, where this function f, okay, take d equal 3, okay, so that means r rho, your order parameter is just 2gm over r, but then you will have logs. I mean, you will have here terms that contain some logs in it. So in a sense, I mean, there's nothing wrong with it. I mean, in a sense, I mean, this is a totally equivalent way to write the Schwarzschild metric, except that you could find it pretty unpleasant to work with that, okay? So, in fact, I mean, this is interesting to see that if you apply the rules of quantum field theory correctly, that means you work in a gauge that is different from that. As I said, I mean, when you go to higher order, you have to compensate for the fact that you are missing the condition from the higher powers of G Newton. This is precisely taken care by the way the gauge invariance is enforced by a gauge fixing term in your amplitude computation. So, in a sense, I mean, yes, it's bad compared to kind of aesthetics or maybe simplicity of the result. What is bad as well is that if you want an all-order result, because you know the Schwarzschild metric is known to all-order and perturbation, the question to how can I get an all-order result from a quantum field theory result, which is actually very, very, it's a question that actually, you know, many people are thinking about that. In a sense, quantum field theory is always a perturbative statement. And you know, there is the question is that perturbative expansion is not generally not summable. I mean, so you cannot sum perturbation because the coefficients diverge and then you have all this non-perturbative effect. It's only an asymptotic series. But in that case, you know that the metric for Schwarzschild is none exactly, right? So is it possible from this quantum field theory result to find a better way to organize your scattering amplitude computation to get it to all order? So bad was actually referring to this in a sense. I mean, working with that Dodonder gauge obscures completely the structure of the generic contribution to high order in G Newton, which means high order in perturbation. So I want just to finish on explaining, so I need 3 slides to explain, I mean, how to redo that metric computation in a different gauge, okay? So if you follow this thing and then you have this object, so the harmonic gauge is the conservation of this, okay? So in fact, there is the square root of G, yeah, right? So you use what Landau-Lifshitz called the inverse, Gothic inverse metric, okay, which is exactly this. And then you have Einstein-Hilbert action. And what you do is that you will have the gauge fixing term that I didn't write. And in fact, there is a very remarkable paper, remarkable because in fact, when it came out, it's already quite old, but I think I didn't appreciate it, how important what this paper was, is that they say that if you take the Einstein-Hilbert action and gauge fix it using the Gothic inverse metric, not work with the Donner gauge, but work with the harmonic gauge, then the action of gravity is purely cubic. So this is an action when you have just a derivative of the metric, so this is this, an auxiliary field, then there's the metric, no derivative, and then auxiliary field. And it's totally equivalent to the Einstein-Hilbert action, the R that I presented before, that normally we all expand near flat space and we get an infinite number of vertices because we have all this inverse metric. Here, this is everything. So you see? And then if you expand in terms of the H with Gothic H, actually upper index, it's only, there's a finite number of vertices. The same way you can couple your action to your massive particle. So in fact, here, because I decided that I have one that is heavy, one that is light, okay, I'm using a language that has a light particle, heavy particle, that is minimally coupled to the metric. And then you see, what I'm saying is that at the end of the day, what you want to do, you want to just compute the equation of motion, okay? You want to compute the equation of motion of these guys in the background of that guy, right? So actually, you want to compute both the equation of motion of both because this one moves, but as well as the interact on the other guy. So the way you do it, it doesn't matter, right? So at the end of the day, everybody should agree on what is the effective action for the equation of motions for your AV, for your 2 black holes. Whether you work with the standard de Donder gauge and what I've explained before, with standard perturbation in flat space, or I work with this inverse Gothic metric and this formalism that is here, right? At the end of the day, everybody has agreed to that. But the thing is that the way you do your integral and the way you integrate your fundamental degrees of freedom matters a lot in the way you are able to do the computation and to which order you can do it. Okay? So, because in the case of when you have a heavy mass and small mass, okay, so one is static and, okay, so there's some expansion you can do. Okay, I'm going to just do. And now what you do is that you redo the computation I described before, which is exactly doing this, okay, emitting a graviton from first the heavy mass one, okay, so there's the, okay, so then I have one heavy mass that emits one graviton, then I have my heavy mass that the graviton interacts emits another graviton, okay, so this is exactly these graphs here that are here, okay. But to the different, but you see, I'm sorry, here you see here there's a 4-point vertex. Okay, so here there's a 4-point vertex, right? Yeah. So here it's only 3-point vertex. So here it's 3-point vertex, 3-point vertex, okay, fine. But here you see that there's already a 4-point vertex. Okay, so which is as well here drawn in a different way. But the thing is that because this is purely cubic, here I only have 3-point vertices. So in fact, because I have only 3-point vertices, it's easy to compute to one order. And even to tell you that at order n, so at order n, so this is here is the number of loops. Okay, so here you see I had a lot of graphs. So here there is a way to write that at arbitrary order n, because everything is purely cubic, I am building it from the previous orders. Okay, so n minus m with only cubic interaction. And okay, so here I don't have any, I emit only a graviton. Okay, so this is the graviton external line, but as well the auxiliary field can propagate. Okay, and of course you can as well look at the emission of the auxiliary field if you want, but okay, if you just want the waveform, I mean the h mu nu, it's only the thing that you need to compute. Okay, so but you need to know as well contribution for the auxiliary field, otherwise you don't have the recursion. So this is a recursion relation, like from a cubic interaction that people are familiar in gauge theory. And then you can solve it. I mean, since because it's very easy, so each terms are easy to compute, you can get to all order. And at the end of the day, you rebuild the coefficient of the metric. Yeah. So the metric, Schwarzschild metric, as this coefficient that you can compute. And then you deduce, you find that there is you get exactly the Schwarzschild metric in the standard coordinate system, as you read in the textbook, to all orders. So yes, okay. So this is one of the things that is remarkable, is that in fact this is exactly showing you the effect of the gauge fixing when you do this quantum field theory approach to compute something very classical. But the other thing is that using this cubic action gives you exactly the background. So in a sense, I mean, at the beginning I was describing flat space computation, and at some point I mean seeing how the flat space is deformed in small perturbation, but I never saw the metric. So in that case, the metric is already building from the fact that I have summed all the contribution from one of the massive objects. So for example, if you go to the next loop order, you can compute at the geodesic equation. So you can, okay, so I'm not going to explain it. I just show a picture. So know that I have built by from my path integral, I know the exact metric. I can look at the next expansion in the mass of this object, the small one, and I'm getting exactly the equation of motion. So this is not an input, this is a derived quantity like that. Okay, so I'm just putting in some references. Okay, I just want to say that maybe I will put my slides available. Yes, I will share my slides. So I'm concluding by the fact that, okay, so let me summarize. So what I have explained. I've explained that there is a quantum field theory formalism that exactly computes what you want to compute in classical GR if you want to compute in the post-Minkowskian expansion. So that means arbitrary velocities and order by order in G Newton between two massive objects that interact gravitationally. To some order in perturbation, that is actually, let's be conservative, like 4 loops, but certainly 5 loops, you can model this way black holes or neutron stars and get exactly what you need for the gravitational waves data that you can feed into an Hamiltonian, which this Hamiltonian will then be used for the analysis of the wave of the data that you get from the interferometers. So in a sense, we are getting accurate formula. This is precision physics. So this is like having reduced the theoretical uncertainty and having some exact expression. And the reason, what is important is that the formalism is such that if you believe that there is some modification of Einstein gravity, that is some extra scalar field, extra field, massless field that couples to your system, you run the same machine and then you can put it and then bingo, you get exactly how it affects the signal. The other point is that the last part of the lecture, which is the self-force computation, insists on the fact that if you do the computation in the correct gauge, I mean, you can get something that is really not a flat space computation, but a curved space computation. And then you really, so that means the geometry of the black hole is not an input, is derived. And in fact, this is important in the context of looking at the dynamics of black holes that are very different masses, when mass M1 is very much smaller than mass M2. So the present day today is actually summarized into what I have online, on screen. So there is the post-Minkowskian expansion that is giving you this amplitude that gives you to an Hamiltonian. It uses quantum field theory scattering amplitude, but in fact, I mean, it works in any effective field theory. So you can go there. Okay. You can do, when you are here, you can do an expansion in small velocity and check that it matches what people have done in post-Newtonian expansion. The gravitational self-force is a nice framework for doing a curved background computation, but it's more, I mean, it's difficult to use if the two masses are comparable, but okay. But at the end of the day, you still get some amplitude that you can feed into the Hamiltonian I described. When perturbation is not good enough, I mean, it's not good anymore, so that means you get to strong coupling problems. Of course, you have to match with numerical GR. And at the end of the day, everything is fit into some something that is called one body formalism that is used for data analysis. So I didn't have time to explain what is the effective one body, but my slides contain something about that. Okay. So this is where we are today, and this is exactly what the field is doing. Okay, so thank you very much for your attention. I will share my slides after I have corrected a few typos. And so there is more on the slide than when I said, but I've as well put some references in case you want to look more. I mean, some of the papers I've mentioned in the talk, but some I didn't. Okay, yet. Thank you.